Okay, let's dive in. We've got this source material, all about ratio and proportion.
Right.
And for you listening, someone who likely follows these ideas, we're not just listing definitions.
No, definitely not.
The goal is to, really unpack it, get to the core insights.
And find what's genuinely useful in these pages. It's quite elegant, actually, how it reveals the links between numbers and quantities.
It really is.
Yeah.
There's a certain clarity it brings.
Yeah.
So right off the bat, the material asks, what is a ratio?
Fundamentally, it's a comparison, a relationship between two quantities.
But there are rules, key rules that the source highlights immediately.
Yes, and this is crucial. The quantities, they have to be of the same kind.
Right. K to K to G, liters to liters.
And importantly, in the same unit. You can't just, compare centimeters to meters without doing something first.
Exactly. The example given is comparing 30 centimeters to 2 meters.
Mm-hmm.
You don't write 30.2. That's meaningless in this context.
You have to convert. So 2 meters becomes 200 centimeters.
And your comparison is 30 centimeters to 200 centimeters.
Which then simplifies. You knock off the units, essentially, divide by 10, you get 3 to 20.
3.20. Simple as that. And that conversion makes the comparison valid. It's consistent.
Precisely. The source also gives us terms. Antecedent for the first number, consequent for the second.
A little bit formal, but good to know.
And it stresses that the ratio itself, that 3.20, it's a pure number.
Ah, right. No units attached to the final ratio.
Because it's expressing a relationship, a scaling factor, not a measurement itself. And you always, always simplify it.
That pure number idea is interesting. It separates a relationship from the actual amounts. Okay, so practical side. How does this help us? The source talks about dividing stuff up.
Yeah, dividing a quantity in a given ratio, a very direct application.
How does that work? Let's say 20 sweets.
Okay, 20 sweets. And you want to share them in a ratio of, say, 2 to 3.
1.3. Right.
The method is quite neat. You sum the parts of the ratio, so 2 plus 3 equals 5.
Could be 5 total parts. That represents the whole share out, kind of.
Exactly. So the first person gets 2 out of those 5 parts. That's 25ths.
And the second gets 3 out of 5 parts, 35ths.
Right. So applied to the 20 sweets, person 1 gets 25 times 20.
Which is 8 sweets.
And person 2 gets 35 times 20.
12 sweets. And 8 plus 12 is 20. Perfect.
It's a clean way to distribute things based on that agreed-upon ratio. Very fair.
Okay, that makes sense. Now, the material naturally transitions from ratio to proportion.
It does. Proportion is presented as simply the equality of two ratios.
So if one ratio is the same as another ratio, they form a proportion.
That's it. If you have 4 numbers and the ratio of the first to the second equals the ratio of the third to the fourth, you've got a proportion.
And we get more terms here.
Hmm?
The first and fourth are called the extremes.
Mm-hmm. The outer numbers.
And the second and third, the middle ones, are the means.
Right. And this is where the source reveals really the core property, the most powerful bit, I think.
Which is?
In any true proportion, the product of the extremes. So first times fourth is always equal to the product of the means. Second times third.
Ah, that rule. Yes, that's the big one. Product of extremes equals product of means.
It's fundamental.
The example provided is 15 is to 20 as 9 is to 12. So 15.2 at 9.02.
Okay, let's test it. Extremes. 15 and 12. 15 times 12 is 180.
Right. And the means 20 and 9. 20 times 9 is also 180.
See, they're equal. 180 equals 180. It confirms the proportion is valid.
It's a check, but it's also a tool, isn't it?
Absolutely. It's how you find a missing value.
Yeah.
The fourth proportional.
Like if you have 3, 4, and 18 and need the fourth number x to make 3.4, 18.x work.
Exactly. You use the rule, extremes, 3 times x means 4 times 18, which is 72.
So 3x equals 72.
Divide by 3 and x is 24.
So 3.4 is proportional to 18.24.
Yeah.
Found it using the rule. Very neat.
Very. The source also mentioned continued proportion briefly.
Oh, yeah, where it's like AB equals BC, the middle term repeats.
Mm-hmm. And that b is called the mean proportional. Like 6 is the mean proportional between 4 and 9.
Because 4.6 is the same as 6.9, both simplified at 2.3.
It just shows how these concepts build.
Okay, so let's sort of wrap up the main threads here. We started with ratios, comparisons needing the same kind, same unit.
And ending up as a pure unitless number, always simplified.
We saw how they help divide quantities fairly, using those fractional parts.
Then we hit proportion, the equality of two ratios.
And the key insight there. The product of the extremes equals the product of the means. A powerful check and problem solver.
These aren't just, textbook exercises. They describe relationships everywhere. Scale, comparison, it's fundamental.
Which really brings us to the final thought for you, the listener. Consider the patterns all around you. Think about maps, recipes, gears on a bike, maybe even how budgets are allocated.
Yeah.
How many of those everyday comparisons and scalings are, at their heart, driven by these very principles of ratio and proportion we just unpacked? Where might you spot these mathematical relationships at work next? Something to ponder.